Okay, thank you, Dr. Parsney, for the great introduction. Today, I'm going to focus on the mechanical behavior of fractures. And at the morning session, I want to focus on the basic principles, basic calculations. And I think that it's really obvious for everyone why studying the fractures is important. It's because of a phenomena we call stress concentration around the fractures and cavities. So I start my lecture about the stress fields around the fractures and cracks. Uh, Whenever you find a cavity, a void space or contact fracture in material, there is always a stress concentration around those cavities. For example, we can assume a circular cavity. Here, we can assume a cavity in which A is equal to B, so a circle. And for example, if we impose a far field stress to this problem, a tensile stress, far field stress on this problem, the theoretical studies and experiments show that if you calculate the stress around the cavity at the edge of the cavity, it's always higher. It's always higher than the far field stress you have applied to the problem. Here, this curve here, for example, the red curve here shows the distribution of sigma yy, the stress component in y direction. And you can see that the far field at infinity is equal to sigma, the far field stress we have applied to the problem. But at the edge of the circle, it's two times the far field stress. And this number 3, which I've shown as a K factor here, is called concentration, the stress concentration factor. It means that then near the circular hole, the stress is 2 times the far field stress after the problem. In general, you can find the stress concentration factor by this relation, which just depends on the aspect ratio of that elliptic hole. I mean, A over B. So when A over B is equal to 1, the K will be equal to 3, which means that the stress concentration factor is equal to 3. But when A over B increases, for example, when B is very smaller than A, K is going to become infinite, yes. The stress concentration factor when A over B is very large increases to infinity. So you can assume that we have a fracture where B over A is 0. So very high aspect ratio. At that case, the stress concentration factor is infinite. Which means that at the crack tip, the stress should be always infinite. I know that it's not realistic, but it's the solution that linear elastic assumptions always give us. So the distribution of the stress near the crack tip is depicted here. In realistic scenario, it cannot happen because you cannot material that can resist, infinite stresses. But theoretically, in brittle materials like rocks, glass, we can always assume this is somehow accurate, distribution of the stress. So this concentration factor is always infinite in fracture mechanics. But for us, the important thing is to find the stress distribution or functional form of the stress variation around the crack tip. Not exactly at the crack tip, around the crack tip. What is the stress field and how it changes? Before starting to study the stress field around the crack tip, I just want to talk about the different modes of fracture. As you know, in three-dimensional space, any force can have three independent components. Yes. And each component of the force, based on the relative direction of the fracture, can create different modes of the fracture. For example, if the component of the force is normal or perpendicular to the fracture, it creates mode 1, we call it opening mode. And it's like in plane displacement field. When I call in plane, I mean the displacement field in XY plane here. If the applied force is parallel to the fracture, the second mode of fracture can develop. And the second mode is also in plane mode. And also we have another mode, third mode, at which the applied force is parallel to the fracture, but it's the out of plane force. I mean, the force in the z direction, normal to the xy plane. Any fracture problem can be decomposed to these three modes, and each mode can be separately, analyzed, because we have already know the exact solution for each mode. So you can always separate your problem to different mode, and then study each mode separately, and then finally combine them together. But sometimes one mode is more dominant. For example, if you have a hydrofracturing process, when it's a process injecting high pressure underground to create fractures in reservoirs, the first mode is the dominant. When you're studying hydrofracturing, you always in an opening mode, so injecting the water and creating opening of the fracture. But when you're studying faults, because at faults, the frictional behavior is more important, you always have combination of second and third modes. Because at second and third modes, you're studying the shear stresses on the fracture of fault. And sliding mode and tearing mode can be combined at those situations. Whenever you tear a paper, you always apply the third mode for tearing the paper. That's why it's called tearing mode. You can consider this paper as an XY plane here, and then I am applying out of plane force paper to tear. So that's why it's called tearing mode, and it's out of plane force applied to the paper. Okay, so let's see. By the way, how we can find the stress field around the crack? It's not easy task, to be honest. Sometimes we need numerical methods, sometimes we still need experimental methods to find the stress field around the fractures. But at some very simple, scenarios, we can find the stress field. And the general approach is to solve the equilibrium equation of any problem in solid mechanics is based on the solving equilibrium equations of the system. So, for example, here it's just the overall approach of how we can find the stress field around the crack tip, and it's based on the third mode, tearing mode. In the third mode, the only unknown you have is the out of plane displacement field you're applying the prop W here. The in plane displacement field, I mean the displacement field in XY plane is 0. U and V is 0, so it's in plane displacement. And the equilibrium equation can be written in polar coordinate, and the crack tip as the origin of these polar coordinates. And I know that Professor Zimmerman has already introduced you the equilibrium equation in polar coordinates, which is based on the r and theta here. R is the distance to the crack tip, and theta is shown here. Anyway, by solving the equation, we have just one unknown here, W. And by solving just one equation, we can find the out-of-plane displacement field. And based on the displacement field, we can also find the out-of-plane shear stresses. In third mode, we just have two non-zero shear stresses, and those shear stresses are out-of-plane shears. The process of solution is not important here. I have explained it last year, but I think it's too much for it. But the approach was proposed by William. He assumed that the solution should have a form like this, which this is the method we usually use in mathematics as a separation of variables. So we separated the final result of the displacement field as a multiplicity, as a one function of r times the one function of theta. So the separation of the variables to r and theta. So yes, we just assume that okay, the final result, the final displacement field should have this functional form, and then substituted this functional form to the equilibrium equation and solve the equilibrium equation to find the f as a function of theta and r to the power of lambda.
What's the value of r?
R is here defined as a distance to the tip, crack tip. So you can assume that we have a polar coordinate system. Its origin is located exactly at the crack tip here. So
The same as the length of the crack is.
no. We are focusing. No. This problem is solved for general fracture. We are not focusing on the length of the fracture right now. We are so close to the crack tip. We are just focusing on the stress field so close to the crack tip, and we ignore the effect of the length here. R is just the distance of a point, and we want to the crack tip. I mean, we want to find the stress at the distance of R and the specific point R and theta. Any questions? The final solution of the problem, I mean the stress field and also the displacement W out of pencils, is these equations here for third mode in polar coordinate and also in Cartesian coordinates. The most important thing for us in this class is the functional form of the stresses and displacement field around the crack. This solution is a dominant term of Williams expansion. And as we can see, we have a function of r, function of theta, which shows the variation of stress as a function of r and theta. The functional form, for example, for third mode, is always the same. I mean, the form is a k constant. If theta here, the function of theta, which is the directional variation of the stress. And also, we always have 1 over the square root of r, which means that the stress goes toward infinity, but with this function. When r is 0, we are at the crack tip. stress is infinite. But it goes toward infinity proportional to the inverse of the square root of, r. It's always the same. I mean, the function of r is always the same, but we have different f theta for different modes. You can see here the f theta for just third mode. The functional form has the same form always. And here the k is very important constant. I can say that it's the most important, characteristic of a stress field around fracture, and it's called a stress intensity factor, K here. K is a function of geometry and loading of the fracture. So the geometry, I mean the fracture length, and also the loading on the fracture, all of them can be reflected in K.
The same as like reduce 1 plus B A over B.
No.
Different K.
It's a different K. It's called the stress intensity factor here. And it shows the intensity of the stress around the crack. Here, when William applied this approach to the problem, we just assumed a crack tip, a general crack tip, but without any loading, without any specific geometry. So his approach can finally lead to such a formula with K as an unknown, because this analysis just gives the general form of the stress. But for finding K, which is very important for us, because I will show that K can also determine the fracture propagation criteria. So for finding K, we should use other approaches that I will just give you one of those, just the simplest one. I think it's very useful just to look at the, the same stress field in other modes. I mean, the mode 1 here. As you can see, if you look at the stress field here, sigma around the crack tip at first mode, for example, the opening mode, you can see that in the first mode, we have two unknowns, and those are the displacement field in x, y plane, u and v. We don't have out of plane displacement in this mode. And the solution of this problem would be more difficult because we have two unknowns. But the final result, final stress field around the crack tip, has the same, functional form. We have the f theta, which for first mode is the same always. The function of f theta is the same. And again, we have here, this is f theta, for example, for sigma xx. And also we have 1 over the square root of r. The square root of r is always there. And k is the stress intensity factor. And we're going to find the which one? Theta.
Yeah,
Theta is the angle is based on the direction to the x, and x is aligned to the fraction. And also you can see here the displacement field. I mean, displacement in x and y directions as a function of r and theta here.
So I guess another way to answer is if you want to find sigma or u at the position r theta, then you use this formula. So the theta and the r are like the input. And the theta and the r move you in the space around the tip. So if you pick r0, you're at the tip. Then if you go a little bit away from the tip, you increase r a little bit, you're at theta 0, you're just in front of the tip. And then the closer you're to the tip, the higher the stress. And then as you go away, the stress reduces. So that just basically describes that behavior. And that's important because that tells you like how the damage is being distributed ahead of the tip, because that stress is damaging your material. Okay.
Just the displacement field, just one point here, depends on the problem that you're problem in plane strain or plane stress. I'm not sure that you are familiar with those terms or not. What the plane strain and plane stress are. Should I explain it? Okay. We usually simplify the three-dimensional problems to two dimensions. You can, for example, assume this one, the first mode of the fracture. The plane stress is those problems, for example, like this paper that I have applied the stress. This paper, if you assume that it's an XY, its plane is XY plane there, in the Z direction, in the direction normal to the XY plane, the thickness of the plate is very small. So for problems which are thin and the thickness is very small, you can assume that, okay, the problem is in plane stress condition, like this paper. And usually we assume that sigma or stress in normal direction to the plane is 0. That's what's called plane stress. On the other hand, plane strain, which is somehow related to problems that in Z direction, in the normal direction to the XY plane, is somehow extended to infinity. In geomechanics, in geological systems, you have a fracture, but in an infinite domain. I mean, the domain is extended to infinity in Z direction. So it's called plane strain. Those problems are plane strain conditions. And yeah, and for second mode also we have the similar but with different theta. I mean, the dependency of theta for the stress field and displacement is different, but the same functional form. So far we have just discussed the functional form, but the most important parameter for us finding the K or certain factor, and finding the K, as I said, is not easy task. And there are different methods for finding K. I just want to explain one of those maybe analytical solutions that can be applied just to specific problems with very simplified loading cases and geometry. But before just explaining the method for finding K, I should just give a small and brief introduction to a concept in the physics, which is called the fundamental solution. The fundamental solution for Green's function. You might be, familiar with this concept if you have passed seismological process, source mechanism, something like that. But the fundamental solution is very important in physics in general, and we can also use it in fracture mechanics. What is the fundamental solution of a system? You can consider this table here in any system, any linear and homogeneous system. I've applied concentrated force like P to this table. So P is known variable for me. I know the external force applied to the table. And I want to find, for example, the stress induced, for example, at this table leg as a function of P. So I want to find the response of the system, for example, at a specific leg of this table, due to a concentrated force P. If I can find this response, I can call it G, Gx. And this G is called the fundamental solution of the problem. The response of the system to a concentrated load. And the G, the response should be absolutely a function of X. X is the location of the force. So if I just change the location of the force, so the stress inside the table leg should be different, yes. Why having the fundamental solution is important? Because if we have the fundamental solution, then we can find the response of the system, I mean, for example, the stress at table leg, to any other arbitrarily loading on the table. If you have the fundamental solution for a system, you can find the response of the system to any other loading cases based on the concept of integration. Because if you have, for example, a distributed load on the table, then you can use the integration concept to finding again the stress at the table leg. Why we can use the integral? Because at the distributed stress, each part of that distributed stress, has a contribution into the stress at the table leg, and we can sum those contributions as integral. So we should consider the intensity of the P, and G is the fundamental solution for green function. This very simple example why it is important. Hopefully, we have the fundamental solution for fracture mechanics for some specific problems, so we can use the fundamental solution for finding the stress intensity factor. I'll show you. Yeah. Just okay. Okay, imagine this problem and just focus on the P, not Q. P on this fracture generates first moment, and Q generates second moment, shear stress. So just focus on the P. So we have a fracture. The fracture has a specific length of 2A. So A here is the half length of the fracture. Okay. And fracture with half length of A is located at an infinite domain. So the domain is extended to infinity at all directions. So a fracture at an infinite domain. And we have applied two concentrated forces because the problem should be in equilibrium states. So we have two concentrated forces, P, at a distance of B. You can see the B and the B. So P is a concentrated force at the fracture faces at a distance of B to the origin. Hopefully, we have the solution for this problem. I mean, we have the stress concentration factor, or K, for this problem. And this problem is a fundamental solution of the fracture mechanics, or for such a fracture. this problem is not a symmetrical problem. So we might expect that the stress concentration on the right fracture tip would be higher than the left one. Yes, because P is applied to on the right side of the fracture. So stress concentration should be higher on the right tip. But instead of right and left, I used the term near and far because it's more clear. So I call this tip, which plus sign here, and call it near tip. I mean the near tip to the P, to the applied force. And the other one with minus sign as a far tip. Far tip and near tip. So in this figure, plus and minus shows the near and far tips of the fracture. And we expect that the stress intensity factor on the right tip will be higher. So K on the right tip is equal to, can you see here or not? I'm not sure. So K on the right tip is equal to 1 over A plus B over A minus B. Okay. But on the left tip, the formula should be A minus B, A plus B. So the first one is a fundamental solution for the right tip or near tip. And the second one is the fundamental solution for the other tip. Those are different and somehow abbreviated in this formula. Okay. Here A in this formula, because this formula is very important in this course, I want to explain it, all details of the formula. In this equation, A is the half length of the fracture. It's a constant here. A is a constant parameter, and it's related to the geometry of the problem. But B is the location of the force. So it somehow shows the dependency of the K or stress intensity factor to the location of the force in the fundamental solution. So if I want to show the dependency of K, I can replace B as an X here and X as a location of the P. So I replace B to somehow show the dependency of K as a function of X. Its location of P, force P. So we have the fundamental solution. And as I said, if we have an arbitrary loading on the crack faces, I can use the integration, find the stress intensity factor to any other problems. So for example, if I have an arbitrary force applied, distributed force applied to crack surfaces, I can integrate from this fundamental solution over X to find the stress intensity factor. For example, K on the right t can be equal to integral fundamental solution here but multiplied by px. Px is the intensity or the function of distributed load acting on the fracture. And integral should be minus a to a over the crack length. We can always use these equations here to find the stress intensity factor for any arbitrary loading. So on the right tip and on the left tip. So it's a very general form of the equation you need for finding the stress intensity. I know that this integral sometimes cannot be solved with analytical mathematical functions, but you can always use a numerical method for a very simple numerical method for calculating this integral. Okay. For some specific symmetrical loadings, it's very important to somehow memorize the final results, final formula for this intensity factor. And because those, loadings happen a lot in the problems. For example, the first one is this loading case. We have two coupled forces applied symmetrical to the fracture surface, but those are concentrated forces. Okay. How we can find the stress concentration factor for this problem based on the fundamental solution? It's very easy. You can always use the superposition because your system is linear and elastic, and you can always combine the stress intensity factor of different loading cases together. So here we have 2p, just a, one p was here, and another one on the other side. The distance of b. Okay. Assume that I want to find the stress intensity factor at the right tip or near tip. There's no near tip here, but the right tip. Okay. There is an effect from P, the near P, on this fracture tip, and another one from the other P, which is far from there. So I should combine the far and near fundamental solution together to find the stress intensity factor at the another right t. But as the problem is symmetrical, so the final result should be the same for the right and left. So by combining the fundamental solution for the near and far tips, and find the stress intensity factor for the symmetrical problem. Any question?
Explain the location for the cathodic fracture.
I will explain it. Okay. If you have the solution for this problem is somehow fundamental solution for a symmetrical loading, okay? You can use this solution as fundamental solution and then use integration to find a stress intensity factor, this loading case, which is a uniform distributed load from distance C to A. C to A, where A is the half length of the fracture. Can use the integration. Absolutely, we integrate from this formula here. And A is always constant. You always integrate over B. You can always assume B as the X and integrate over formula here to find the stress intensity factor for sloping case. And finally, as a very important case, necessary case of this formula, when C is equal to 0, I think so. You have a fracture. You have a fracture with half length of A and uniform distributed loading of sigma applied to fracture surface. So for this case, K or stress intensity factor is a specific case, C equal to 0, and it will be sigma times square root of P by A. And it's very important formula. Always remember this stress intensity factor. It's very simple formula. Sigma square root of PA. And it shows the stress intensity factor for a fracture located in infinite domain. We can go for a break and